Hello, viewers. Waiting for a few more people to join up. Let's see how many viewers I have now. Eating beans. Does that mean you are tooting? Gonna wait for a few more people. Okay, I'm gonna start. Good morning, everyone. Whoa, looking at the temperature, it's climbing above 90. All right, so today we are going to have a second lesson on projectile motion. Okay? So let me just do a little review of what we learned last time. Projectile motion review. The first thing we discussed is if you have a diagonal velocity, a diagonal launch speed, so you launch a projectile with an initial speed v0 at an angle theta. Part of that velocity is vertical, so we called that vy0. And part of that, hello Diego. And part of that initial velocity is horizontal, so we'll call that vx0. Okay? And we use trigonometry to get the values of those initial x and y velocities. So vy0 we can see is opposite the angle, so that's going to be the sine function. v0 sine of theta. And the horizontal component is adjacent to the angle, so that's going to be cosine. Okay? So that's generally, if you have an angled launch, that's generally the first thing you're going to do, is you're going to get the initial components of the velocity. Alternatively, and this is in the quiz today, if you know the components of the initial velocity, you could get the launch speed from the Pythagorean theorem. Okay? Just like if you have a 3, 4, 5 triangle, if you know that one side is 3 and the other side is 4, you can do the Pythagorean theorem and get 5 as the hypotenuse. All right. And then we went on to learn the equations of projectile motion. So there were two of them. Delta x is Vx naught times time. Okay. And delta y is the y naught times time minus 1/2 g t squared. Okay. So notice how there's no t squared term in delta x because gravity pulls vertically, not horizontally. So we have no acceleration term for the delta x. Last time we applied these equations to two problems. One of the problems that we applied it to was horizontal launch off a cliff. Okay, so that was the problem where we had the mixtape that was thrown off the cliff like so, and it went like that. And we calculated how far it goes, and then we calculated the distance it goes in that time. The second problem that we did was a problem with an angled launch across a level surface. And so for that, we had the example problem was a sniper who fires a projectile, and it goes in a parabolic arc, and we calculated how far it goes. Okay? For both of these problems, the general strategy was to find the time of flight from one equation and then we plugged that time in the second equation. Okay? So we use one of the equations to get the time, then we use the other one to get a distance. Generally speaking, that's how you would solve these problems. Okay? So now we're going to do some newer stuff. So we're going to do two examples, and then we're going to learn some more theory. Okay? So the first example is you are egging a rival's house. You stand you stand 20 meters in front of the house. Okay. You throw the egg at 18 meters per second with angle, let's say 50 degrees above the horizontal. Where does the egg hit the house? Okay. Where does the egg hit the house? So let's draw a picture of what this looks like. We've got our house. It's got some windows. It's got a door. Okay, so here's your rival's house. And here's you. You throw the egg. And it hits the house. That. You are standing 20 meters in front of the house. Okay? And we want to know, where does it hit the house? So what I'm asking for is delta y. What is the delta y of the egg when it reaches the house? Okay? So first step always in these problems, if you have an angled launch, is you want to get the components. Okay? So you have an 18 meter per second launch at 50 degrees. So to get the vertical component, I'm going to type in 18 times sine of theta. I'm in degree mode, and that's about 13.8 meters per second. And then the horizontal component of the velocity is going to be 18 times cosine of 50, which is 11.6 meters per second. So now that I have those, I can write the equations of projectile motion. There's going to be two of them. There is delta x equals Vx naught times time. It's right up here. So that's going to be delta x equals 11.6 t. And then we're going to have a delta y equation, which is delta y equals Vy naught, 13.8 t, minus 1/2 gt squared. This is an egging that is happening on Earth. Okay? This is an egging that is happening on Earth. So 1/2 a is going to be -5. All right? So those are our two equations of projectile motion. Now, who can tell me what mathematical condition, so like, for example, here in the horizontal launch off a cliff, we knew that the projectile had reached the ground when we had delta y equals a certain value, okay? Actually, delta y was less than 0, but when we reached a certain delta y value, we knew we had hit the ground, okay? For this problem, we have delta y equals 0 is when we hit the ground because we came back to the same elevation. Now, what is the condition, the mathematical condition that tells us we have reached the house? And I'll wait until someone types it in. Dum-de-dum-de-dum. There's a certain time when it reaches the house, but how are we going to calculate what that time is? Okay. So for example, in this problem, we said delta y equals -5 meters or whatever. Exactly. So when it has gone 20 meters, okay? So when delta x equals 20 meters, we know that it has hit the house. So this is our condition. So we're going to plug in 20 for delta x. So we have 20 equals 11.6 t. And we solve for time. So the time of flight is 20 over 11.6. .7 seconds. That is the time of flight. So this problem was a little different because in these two problems, we used our delta y equation first to find the time of flight. But in this one, we use the delta x equation to find the time of flight. So it depends on the situation, which equation you're going to use first. Then I plug that time into the delta y equation. So I have delta y as 13.8 times 1.7 minus 5 times 1.7 squared. And I can get the delta y value. So 13.8 times 1.7 minus 5 times 1.7 squared gives us 9 meters on the dot. delta y equals 9 meters. And that's our answer. I have two questions for you. My first question is, so that means it's going to hit the house 9 meters up from the ground. So my first question is, what if the house is 7 meters tall? What does that mean? So I'm going to type that into the live chat. What if the house is 7 meters tall, in this case? And my second question is, what if we had calculated that delta y is less than 0? Good. So people are correctly answering my first question. So if the house is only 7 meters tall, then the egg isn't. It could hit the roof of the house on the way down, or it could just completely go over the house. So that it kind of depends on the shape of the roof of the house and how wide the house is. If you get that delta y is negative, then that means that the projectile would do something like this. It goes down here, which is another way of saying that it hit the ground before it reached the house. Excellent. Very good. Okay, so let's do a second example for today. So for this example, we have a mortar is launched with speed (70 meters per second) at angle 45 degrees. Go ahead and type it into the live chat if you know what is special about 45 degrees compared to other angles in terms of trigonometry. From a cliff of height 130 meters. Okay, so let me draw a picture of what that would look like. We've got a cliff. The cliff is 130 meters tall. There's a question, is it 1.7 in the first example? Yes. 130 meters tall. And we launch the projectile at an angle of 45 degrees, 70 meters per second. The projectile goes up like this. And I want to know two things. The first thing I want to know is how far does it go? And the second thing I want to know is how high does it go? Okay? Now this problem is a mixture of the two problems we did last time, because we did a problem that was a horizontal launch off a cliff. So this is a launch that is off a cliff. So in that sense, it is like the first problem, but it is also an angled launch. So in that sense, it's like the second problem. Okay? So first thing we want to do is we want to get our initial y velocity and our initial x velocity. So we have 70 meters per second and 45 degrees. Okay, so to get the vertical component, I have 70 times sine of 45, which is about 49.5 meters per second. Okay, now the thing that is special about 45 degrees, and some of you have answered it correctly in the chat, is that 45 degrees is an equal balance between vertical and horizontal velocities. Okay, So that means that we don't even have to do the second calculation because we automatically know it's 49.5. If you have an initial velocity that is less than 45 degrees, so something like this, it is more horizontal than vertical. And if you have a launch that is like this, it is more vertical than horizontal. So 45 degrees is where you have balance between, you have equal vertical velocity and horizontal velocity, okay? So now we're going to get our delta x equation and our delta y equation. So delta x is Vx naught times time, so 49.5 t. Delta y is Vy naught times time, 49.5 t, minus 5t squared, okay? So what is the mathematical condition that means that the mortar hits the ground? Type it into the live chat if you know. I will wait. We don't have delta y equals 0 in this problem. Why is that? Well, delta y equals 0 means that it returns to the same elevation that it started at. So this, if we started the mortar here and we stopped the problem here, that would be a delta y equals 0 because we have the same elevation. But for this problem, it actually drops and it hits the ground after falling 130 meters. So we're going to have delta y as negative 130. Okay. So I will add 130 to both sides. We get 0 equals 130 plus 49.5 t minus 5t squared. Okay? So this is a quadratic equation. So how are we going to solve a quadratic equation? We use the quadratic formula, or we can use Desmos. All right? So I choose the latter, Desmos. So you can see I have y in meters versus time. And so I'm going to type in the equation. Y equals 130 plus 49.5 t minus 5t squared. And you can see that we get a downward parabola. And so we're trying to see when is this parabola equal to 0. So I need the zeros of the parabola, which are right here and right here. Notice that one of the times is negative. That is unphysical. We would say it's unphysical because the mortar doesn't land in the past. It lands in the future, so our time elapsed is positive, and we can see that the time at which we reach the ground is at about 12 seconds. Okay? So based on this, we get that the time is 12 seconds. Okay? Which we can then plug into our x equation. So 49.5 times 12, kind of running out of space here. 49.5 times 12 is 594 meters. So that means that this projectile is going to go 594 meters horizontally before it hits the ground. Another nice thing we can do from this graph is we can calculate how, or we can see how high it's going to go, because we can see at time 0, the altitude of the projectile is 130. All right. So if we want to know what was the maximum altitude, we just go to the apex of the parabola, and we can see that the y-coordinate is 252, about 253 meters. So what that means is that the projectile goes 253 meters into the air, like so. All right? So those are 2 additional examples with projectile motion. Let's go ahead and learn a little bit more theory, okay? So this part of the lesson is about motion graphs in projectile motion, okay? So how do we do motion graphs in projectile motion? Well, you might remember that if we have one-dimensional motion, one of the graphs that we made was a velocity time graph. Okay, that's for one-dimensional motion. For two-dimensional motion, we are going to have 2 velocity time graphs. One of the velocity time graphs is for the horizontal part of the velocity versus time, the x versus time. And the other one is for the y component of the velocity versus time. Okay, so if we had 3-dimensional motion, we would have 3 velocity graphs. We would have an x part of the velocity, a y part of the velocity, and a z part of the velocity. So the number of velocity graphs we need is equal to the number of dimensions that the thing is moving through, okay? So what do these graphs look like in projectile motion? The x velocity of the projectile is steady. It's constant. So its graph looks like this. It looks like a horizontal line. Now, why is that? That is because gravity does not cause any horizontal acceleration. Gravity pulls vertically. So gravity can change the vertical part of the velocity, but it cannot change the horizontal part of the velocity. Okay? So this one is just a flat line of slope 0. Okay? Gravity doesn't pull horizontally. The y component of the velocity does change as time goes on. Okay, it looks like this. Why does it slope down? It's because gravity makes the velocity more and more negative as time goes on. Okay? It makes the velocity go more and more negative as time goes on. Eventually, if you throw something up into the air, it has a positive y velocity, but eventually gravity pulls it back down and it has a negative y velocity. Okay? Just like the slope of a velocity time graph is acceleration, the slope of the y velocity versus time is the acceleration. And because projectile motion is driven by gravity, it's the acceleration due to gravity. Gravity. Okay? The other thing we could do is we could look at what is happening at time 0. The intercepts of these graphs are the initial values of the velocity. So this is the initial x velocity, and this is the initial y velocity. Okay? So that tells us the initial y velocity, initial x velocity. Okay? And we could actually use these two values to determine the launch speed. Okay? If you know the two legs of a right triangle, if you know the two legs of a right triangle, then you can get the hypotenuse, which is the launch speed, using the Pythagorean theorem. Okay? Similarly, if you knew the two components of the so we have a question. What would happen if there were two positive zeros? There will never be two positive zeros. One is always going to be positive and one is negative. If you got two positive zeros, then you set up the problem wrong. Interesting question. How would we get the angle? Well, we could actually, have you guys ever used an arctangent before, or an inverse tangent? So if we wanted to get the angle, we could do an inverse tangent of Vy naught over Vx naught. Okay. Now let's go ahead and talk about when is the projectile at its highest point? Okay. Type it into the live chat if you remember in the geyser problem. How did we know that the stream of water that came out of Old Faithful, how did we know that the stream out of Old Faithful had reached its apex? We had a certain mathematical condition. I'll wait for someone to type it in. It wasn't half the time. That you got to be a little bit careful. It's not half the time if it's an asymmetrical problem. So like consider this Desmos problem that we just did. It reaches its apex at around 5 seconds. Okay? But it hits the ground in 12 seconds. So if you have an angled launch off a cliff, the highest point doesn't happen at the midpoint. It happens when the parabola reaches its maximum, which might not be in the middle. Okay? Because really this parabola only exists for times greater than 0. So I should say, time greater than 0, something like this. Okay? All right, let's see. So, so at the highest point, we had velocity is 0. So how does that change in 2 dimensions? Well, in 2 dimensions, Vy equals 0 at the highest point. Okay? So this is a slight difference from one-dimensional motion. Why is that? Well, if you are in an arc, okay, and you are at your highest point in the arc, what would it mean if your velocity was 0 at the highest point, both x and y velocity? If both x and y velocity were 0 at the highest point, then the projectile would just drop straight down, okay, after reaching the highest point. But because the projectile is continuing horizontally past the highest point, it only has horizontal velocity at the highest point, okay? So at the highest point, the velocity is entirely horizontal. Okay? So That's an important point. At the highest point, the velocity is entirely horizontal. So the velocity at the apex is equal to the horizontal velocity. But, interestingly enough, if we go to the horizontal velocity graph, the horizontal velocity never changes because gravity doesn't pull horizontally. So the velocity at the apex is actually equal to the initial horizontal velocity. Okay? So these are kind of some important factoids for two-dimensional motion that are slightly different from one-dimensional motion. Okay? All right, so let's do an example with some motion graphs. So what if I had two velocity time graphs? So I have an x velocity versus time. So v sub x measured in meters per second. Time measured in seconds. All right. And then I have a y velocity graph in meters per second, 0. Okay, so let me draw what these look like. That's what these graphs look like. And let's say that this graph starts at 20 meters per second. This graph starts at 90 meters per second. And it reaches 0 at 4 seconds. So this is not a launch on Earth, okay? This acceleration is not -10, okay? So let's just go through some questions here. My first question is, what is Vx naught? Well, in this example, Vx naught would be the starting value of the horizontal velocity. So I go to my horizontal velocity graph, and I can see it starts at 20. It is always 20 because the horizontal velocity doesn't change in projectile motion. So Vx naught is 20 meters per second. What is Vy naught? Vy naught is going to be the speed, or the y component of the velocity at time 0. So that would be at time 0, our y velocity is 90 meters per second. Okay? What is the launch speed? So to get the launch speed, if I look at my initial velocity triangle, okay, it goes up 90 and it goes over 20. So how can I get the hypotenuse of that? I would use the Pythagorean theorem, okay? So I'm going to do the square root of 20 squared plus 90 squared, which is 92 meters per second. So the launch speed is about 92 meters per second. Okay. What is the launch angle based on this? Well, the launch angle would be this. And so I can see that tangent of theta is opposite over adjacent. So that would be 90 over 20. Or 9 over 2, canceling out the 10. So to get the launch angle, we would do an inverse tangent. So I have inverse tangent of 90 over 20 is 77 degrees. Notice how the vertical velocity is much greater than the horizontal velocity, so it's a almost up and down launch, okay? If they were equal, this would be a 45-degree launch. What is the acceleration due to gravity on this planet? To do that, to figure out the acceleration due to gravity, I want the slope of the y velocity graph. Okay, So I'm going to get the slope of this graph. I can see that this graph goes down 90 and it goes over 4. Okay, so negative 90 over 4 is the slope, which is negative 22.5 meters per second squared is the acceleration due to gravity. What is the time at which we reach the apex? As I said before, in 2 dimensions, the y velocity is 0 at the highest point. Okay, so looking at our y velocity graph, I can see it becomes 0 at 4 seconds. So the apex is at 4 seconds. And then lastly, what is the speed at the apex? Well, at the apex, there is no vertical velocity. All of the velocity is horizontal. And the horizontal velocity doesn't change from the value it had when the projectile was launched. Okay, so it's just Vx naught. So the speed at the apex is going to be 20 meters per second. All right. So there you have it, class. That's my lesson for today, and I will see you in the Zoom room. See you in just a few.